Yeah, good morning. Good morning, everybody. First of all, let me thank all the organizers that put this workshop together. It's wonderful. And of course, thanks, Allan, for allowing for this workshop. So, yeah. Well, actually, I'm a little confused now because I thought at these events where we celebrate the icons, we should show at least a couple of silly pictures, right? But Hideo didn't do it and Chen didn't do it. So, and you guys are much more experienced than I. So I don't know. But anyway, let me just show this one because I thought, it's the time of the year, right? So it's okay. It's a nice picture. And plus I wanted to just wish you happy holidays, Merry Christmas. And I'm so happy that I can be here in person this year. So I probably should not show this one. But I was just, Cairo gave it to me yesterday, and he's sending the warmest regards also, so I have to show it. Right, so this is the title of the talk, and the talk will be partly based on this recent review article that we put together with Allan and also with two of our close colleagues in Europe, in Germany, and also with these folks from Illinois. But before I get to ultramagnets, it's just one flashback 25 years back. I am arriving to not Austin yet, to Bloomington with my PhD degree, just fresh PhD degree in my hand. I arrived to Allan's office and he's saying, why don't you start working on spintronics? And he said, there is an interesting guy in Japan named Hideo Ono, and you should particularly follow and look what this guy is doing. And so we started working on spintronics 25 years ago. And so Hideo told you all about the technology of spintronics, but for us physicists, Hideo is obviously a physicist as well. Sorry, that was not meant as an insult. Theoretical physicist by training, that's what I meant. Magnetism is just a state where you spontaneously break the spin rotation symmetry. And how you can test it in a spintronic device that when you rotate spin, the state is different is to place another reference ferromagnet and then run these electrical currents, which in ferromagnets are spin polarized, and they will recognize that there is a difference in these two guys, even though the only difference is a rotation of spin. Now, at the same time, Allan and Steve, I don't know if Steve is already here. Yeah, hi. They came to me and they say, there is another very interesting experimentalist I think at that time still at Bell Labs. Is Jim Eisenstein already here? It's coming tomorrow, probably coming tomorrow. And that this guy was just working on experiments, seeing a very awkward feature that a 2D electron system, because of electron-electron interaction, spontaneously breaks real space rotation symmetry. And today we call these systems electronic nematics. So what happens is that without interactions, you just have a Fermi surface which respects the rotation symmetries of your system. So it's spherical in a crudest approximation. Now electron-electron interactions squish the Fermi surface and create a spontaneously broken real space rotation symmetry. So at that time, I was just a fresh PhD graduate. I thought that in condensed matter, there couldn't be more remote areas than spintronics and electronic nematics. So now, 25 years later, we have ultramagnets. And remarkably, ultramagnets seem to connect these two worlds in one physical system. So let's take a look at what ultramagnets are. So first, from the spintronics perspective. So we have a magnet. It's a magnetically ordered system. So it spontaneously breaks rotation symmetry, but now it's different from the conventional ferromagnets because half of the spins in the magnets are pointing up and the other half of the spins are pointing down. So you can have an arrangement of up-down representing logic 0, but you can also have an opposite arrangement, the spin space reversed arrangement of down-up. There are two different states. They should represent 0 and 1, but how am I going to measure it? How am I going to sense the difference if I don't have spin polarized currents? Because obviously I have the same number of spin ups and spin downs. There shouldn't be any spin polarized currents. No, it's wrong. When I run electrical current, it is actually strongly spin polarized. In one case, it's primarily spin ups carrying the electrical current. In the other case, it's primarily spin downs. So what's the trick? The trick is that these ultramagnets do not only break spontaneously the spin space rotation symmetry, but they also break the real space rotation symmetry. And again, still within the spintronics language, how does it look like? When I run electrical current along one crystallographic direction, I get the spin up polarized current. Now in the same state, when I now run electrical current along an equivalent crystallographic direction, but orthogonal, it's actually the opposite spin that is carrying the electrical current. Now, when I run the electrical current at a diagonal direction, I have 0 spin polarization. Both spins are actually carrying the electrical current. So that's the spintronics cartoon. Now the cartoon on the theoretical physics, on the Fermi surfaces. What happens is that in the normal state of an ultramagnet, I have two degenerate Fermi surfaces that respect the symmetry of the crystal. If the crystal is cubic, it will have a cubic symmetry. Now, when it switches to the magnetically ordered state below the transition temperature, what happens is that the Fermi surfaces get squished, just like in the electronic nematic. The difference, though, is that I have spin up and spin down Fermi surfaces, and they get squished in an orthogonal direction. So I'm not just getting a nematic state, but it's also a spin polarized nematic state or spin ordered nematic state. So this was on the cartoon level, but how do the real materials look like that can actually house this, this type of phase that breaks simultaneously real space and spin space rotation symmetry? So this is an example of a real material that can house this phase. And it's a real material now shown the crystal lattice in the normal state. And what you see, it has a perfect cubic symmetry. But when it undergoes the phase transition into the magnetically ordered state, this is what happens. I have a spin arrangement now, which breaks the cubic symmetry because my downspins here are arranged along this direction. And you see along the line, there are these non-magnetic atoms. While in the orthogonal direction for the spin downs, there are no non-magnetic atoms. But now if you look at the upspins, in the horizontal direction, they do not have the non-magnetic atoms in between, while for the orthogonal or this vertical direction, they do have the non-magnetic atoms. So the ordering is such that it breaks spontaneously the real space rotation symmetry. Now, to make the correspondence between the momentum space and the real space even more obvious, you can take a look at the real space spin densities as viewed from the central non-magnetic atom. And what you see is that the spin densities here are largely anisotropic because of the presence of the non-magnetic atoms. Now, if I would have looked at the spin density from this non-magnetic atom, it would look like exactly the same. So the nature of ultramagnets is that it actually does not have an antiferroic order. It has a ferroic order. It's like a ferromagnet, if you want. This shape of the spin density is repeating ferroically on every equivalent site on the crystal lattice here. Now, there's one thing that you have to make sure that your crystal lattice does not have in order to have these spin split or spin polarized Fermi surfaces, and that would be a translation symmetry connecting the opposite sign spin densities. If there were a translation symmetries that would connect these opposite sign spin densities, you will have a spin-degenerate Fermi surface. Simultaneously, you have to also make sure that they are not connected by inversion. So translation or inversion is a killer. But as long as your lattice does not have these symmetries, you're good. You can have spin polarized Fermi surfaces. Now, what we have in our ultramagnets is that we break the translation and inversion symmetries connecting the two sublattices, but we still have one crystallographic symmetry left that connects them, and that's a crystal rotation. So in this cubic lattice, it would be this fourfold or 90-degree crystal rotation that connects the opposite spin sublattices. So written in the language of spin groups that Chin described in his morning talk, we have a symmetry in the crystal, which is a combination of a twofold 180-degree spin space rotation with a crystal rotation. It could be any, but on our model lattice, it's a fourfold crystal rotation symmetry. Combining these two different rotation transformations is the defining symmetry of our ultramagnet. So it's not only the breaking of the symmetries that is important, but it's also the symmetry that is preserved in the ordered phase, which is very important for defining the state. Why is it so important? Because having this symmetry connecting the opposite spins guarantees that there is absolutely zero net magnetization. It just guarantees that the system is fully compensated. Simultaneously, it does allow for the spin polarization, and it does allow for the spin polarization in a way that it breaks time reversal symmetry. If I look at the momentum here, now I time reverse it to the opposite momentum, I see the same spin. And that means that time reversal symmetry is broken. And that's also a very important defining feature of ultramagnets. It's not only the spin space rotation, real space rotation symmetries are broken, but also time reversal symmetry is broken, but simultaneously at a vanishing or zero net magnetization. Now, the question that we asked here in this perspective or review article is, is that type of spontaneous symmetry breaking something that is actually common in condensed matter? Are there many examples? And well, there is definitely one very well known and very well established example of a symmetry breaking phase that actually has exactly the same properties that I just described to you. And that's the A phase of superfluid helium-3. So the A phase of superfluid helium-3 spontaneously breaks the spin space rotation symmetry, the real space rotation symmetry. It breaks time reversal symmetry, and it has vanishing net magnetization. So all the characteristic feature of ultramagnets are shared with the superfluid helium-3. Why is it so? Because in superfluid helium-3, we have non-zero angular momentum pairing, and that makes the phase anisotropic in the real space, meaning it breaks the real space rotation symmetry. Simultaneously, it is a spin singlet pairing, and the Cooper pair is a superposition of states which have the same sign of the z component of the angular momentum and opposite sign of the z component of the spin. And because of this, we have no net magnetization. But we do break spin space rotation symmetry, and we do break the real space rotation symmetry. So in terms of symmetry of the ordering, they are equivalent or they are counterpart phases, but microscopically, there is a huge difference. In superfluid helium-3, the microscopic mechanism that is responsible for this A phase of superfluid helium-3 is a very subtle pairing-dependent ferromagnetic fluctuations mechanism. And because it's a subtle mechanism, it's not very easy to stabilize this phase. It's actually stabilized only in a very narrow phase space of external parameters around 2 millikelvin and 30 bars of pressure. So it's a very delicate phase, and also is very rare. Now, in ultramagnets, the microscopic physics is completely different. What stabilizes the phase of ultramagnets is a combination of a robust Coulomb exchange interaction with another robust interaction, and that's of electrons with the ionic potential of the crystal lattice. And because they are both robust, you can stabilize this phase at ambient conditions in many crystals, and it's abundant among the magnetically ordered systems. So, so that was a bit of a theory, but condensed matter physics is an experimental physics or science in the end. So you need to have an experiments that prove this. And so here are some recent direct experimental observation of this ultramagnetic phase, both in band structure spectroscopy and also in real space microscopy. So starting from the microscopy, I mentioned that ultramagnets break time reversal symmetry. And that's very nice because it gives us, and strongly breaks the time reversal symmetry as strongly as ferromagnets. So we can use the tools that we're used to use in ferromagnets to directly image magnetization on a microscopic scale, on a submicron 10 nanometer resolution scale. And that's X-ray magnetic circular diaprism combined with the photo emission electron microscopy. So here are the images using exactly the same technique. The only difference now is that we are not vector mapping the magnetization. The vectors, the white vectors here, are the nail vectors in our ultramagnet. And for the material itself, we chose something that is arguably the simplest possible material. It's just a simple binary compound of manganese and tellurium, which is a material that orders at room temperature. And it has these ultramagnetic symmetries combined into two-fold spin space rotation. Now in this time, because it's a hexagonal crystal combined with a six-fold real space rotation symmetry. This is the ultramagnetic defining symmetry. And because it breaks time reversal symmetry, we can use this technique and we can do the direct mapping with the resolution. I forgot to put the scale here, but it's about 10 nanometers. So we have about 10 nanometers of resolution of the full vector mapping of the nail vector in our system, not magnetization, but the nail vector. And you can see these marons, anti-maron pairs. You can see domain walls, domains, etc. What would be very important for spintronics, but also for many other experimental exploration, is the ability to prepare those ultramagnets in a single domain state. So this is what we showed on these images. Now it's a few micron scale where we can show that we can prepare the state in a single domain ultramagnetic phase. Now this is very important if you want to do, for example, an angular result photo emission spectroscopy and look at the bands and their spin polarization. So this is being done in this work where you see these time reversal breaking, spin splitting in the bands of this ultramagnet. So I started with a flashback 25 years ago and went straight to today. But you know, you might be wondering, was there anything happening in between these 25 years? And you know, the answer is yes. There's been lots of studies that actually helped us to get where we are here today. And you know, all these studies, virtually all these studies, were inspired by what Allan is actually thinking and doing over these 25 years. When I told you that when I just arrived to Bloomington, Allan told me, just why didn't you start working on spintronics? He was not that interested in these spin polarized electrical currents that are used in the commercial spintronic devices. He was more intrigued by what is the microscopic physics origin of anomalous Hall effect, because at that time it was a bit of a mystery. And together with Chin, they just had an idea that it could be related to this Berry curvature. And so we took a look at this, did the calculations. It was a sizable effect. And more importantly, the size was actually matching what Hideo was doing at that time, measuring the anomalous Hall effect in ferromagnetic gallium manganese arsenide. So this was very encouraging. And it actually very directly led, now with Haru Sinoa joining the crew, to the prediction of the spin Hall effect, which was a sibling effect, again, originating from this very similar spin orbit coupling physics. So now we had ferromagnetic spintronics, now spin Hall effect, starting the so-called spin orbitronics in non-magnetic systems. So we have ferromagnets, non-magnets, what's left? And it looked like the only thing that was left was spintronics in antiferromagnets. So Allan obviously suggested the whole concept of spintronics based on anti-ferromagnets, and the way how to control and read the antiferromagnetic order in these papers actually worked together with Rembert, who I believe is in the audience, right? Was to take advantage of the staggered exchange fields. But what they've also immediately figured out that these phenomena are subtle, coherent interface effects, which were very clever theoretically, but experimentally challenging. So we move in time by maybe a decade when we started looking into the problem, and we said, so if it's experimentally challenging to realize antiferromagnetic spintronics based on the staggered exchange fields, why don't we try to do it based on staggered spin-orbit fields, Chin's world, getting inspired from the spin-Hall effect. Because in spin-Hall effect, we know that we can, just by spin-orbit coupling, generate fields or spin polarization with opposite sign at these opposite edges, which have the opposite sense of breaking real space inversion symmetry. So we took an antiferromagnetic crystals and started thinking, if we can find sites inside, microscopic sites in the crystal, which locally break the inversion symmetry, and if the sense of the local inversion symmetry breaking is opposite at these two sites, like in the spin-Hall effect, by running electrical current, we should be able to generate these staggered spin-orbit polarizations or spin-orbit fields. And if simultaneously those sites happen to be occupied in equilibrium by the opposite magnetic moments of the antiferromagnet, we have what we need, a staggered field acting on staggered order, and it should be able to switch it. And it did. Actually, very first experiments were successful, and over a couple of years, we were able to demonstrate this operating antiferromagnetic bit even on a USB stick attached to a computer. And because it's an antiferromagnet, it has much faster dynamics. We could also demonstrate that the switching can be done within 1 picosecond by applying, instead of current pulses, terahertz pulses. But again, there is a problem. And the problem is that these phenomena are based on spin-orbit coupling. And as Chin explained, these are intrinsically weak effects. That this is part of the problem also of the SOT MRAMs, where it is still not commercial. They are relatively weak effects. So we kept staring for decades at this antiferromagnetic crystal lattice and thinking, how come we cannot get the spins out of the crystal just from one sublattice when we run the electrical current and not from the other? And of course, 10 years back, we convinced ourselves it's simply the symmetry of every antiferromagnet that prohibits this, that you will always get both spins when you carry an electrical current, unless you have an ultramagnet. In an ultramagnet, when you run electrical current, you predominantly get just one spin, but it's predominantly only one sublattice is active when you run a global electrical current. So we got exactly what we wanted. Of course, this is just theoretical spintronic concepts. We have first demonstrations that the phase exists, but whether this is really viable for not even thinking of commercial, but experimental spintronics is something that we need to work on now. So this brings me to the concluding slide. So the conclusions is very simple. It's been a fantastic fun over the 25 years in physics, and because of Allan, and because of all his insights and guidance. And so Allan, thanks a lot. Wonderful. But let's forget about past and let's look forward for the next 25 years. And I think there's a lot of exciting physics, and hopefully maybe ultramagnets could be part of it. Why? Because if you look at the menu, it's actually quite rich. There are many materials: insulating, semiconducting, metallic, superconducting, multiferric, topological, 3D, 2D, even layered. And if you need, we can twist them. Okay. Now, we also know now that they're not even the even parity magnets like the D wave, G wave, and I wave ultramagnets, but we also now know the recipe how to look for the odd parity magnets P wave or F wave, which now actually do not break time reversal symmetry. They are time reversal invariant, but they have spin splitting. So it's something like a Rajba system, but not because of spin orbit coupling, but because of exchange. And if you now look into the materials table, you will figure out that yes, the good conventional antiferromagnets, they're everywhere. But if you look at ultramagnets or these odd parity magnets, there's more of them than of the ferromagnets. So there looks like a big playground to play with for the next 25 years. And I hope there will be at least some overlap with Allan. So Allan, thanks a lot.
So thank you for the very, very nice talk and picture. So I'm interested in this lattice. So obviously it looks like the Lieb lattice, right? And then if I just had, on-site Hubbard U, I would expect that to ferromagnetize rather than do altermagnetism, right? So do you know the conditions on the interaction that it would do? It would go into the altermagnet rather than the ferromagnetic flat band usual type of story.
No, I don't know exactly the conditions, but I know of a few materials which from neutrons, we know that they actually have this antiparallel compensated order. So it does exist. It's not just
of course.
An academic exercise, but this is a very good question, the role of correlations. So my general answer to this is that ultramagnets, we have examples of ultramagnets across the entire range of strengths of correlations. We have very weakly correlated metallic ones where when we do DFT calculation, we don't have to even include U. It's just a pure LDA and you have nice order. There are others where they're actually strongly correlated, and there are some where correlations are fundamental because without them, yes, it would be antiparallel, but it would be a conventional antiferromagnet, and only correlations make orbital ordering on top of this, and that breaks the additional symmetry. So correlations are really a lot of fun physics to that to explore. But that's just a general answer.
Should I stay away from flat bands, or like, for example, for this Lieb lattice, is it, of course, if I just have nearest neighbors, I'll have flat bands. But if I are flat bands bad or good for altermagnets with the appropriate interaction? What do you think?
Well, it depends. I think they could be bad and good if you are interested in interplay of ultramagnetism with unconventional superconductivity, which we are. And for example, lanthanum copper oxide happens to be an ultramagnet. So I think if you want to look into systems where strong correlations are important, like unconventional superconductivity, for example, then flat bands and that physics is good. But if you want to talk about spintronics, nice metallic, weakly correlated systems, then it's a different story. I guess it depends on the context. The nice thing is ultramagnets seem to be available across the whole range of correlations.
Thank you very much. Very, very interesting.
Yeah, I have a question. You showed this diachronism, right?
Yeah.
Mapping, right? You had a slide. Yeah. Here, does this require spin orbit coupling, or actually the ultramagnetic state, is that enough to have this?
So you know very well from symmetry, as long as you have a collinear system or a coplanar, to have anomalous Hall type of response like Hall effect, Kerr effect, MCD, you need spin orbit coupling. But there is a but, interesting but actually. In the transport anomalous Hall effect, the DC transport, it's actually very hard to disentangle, symmetry-wise, the same conditions for magnetization and anomalous Hall effect. It's an axial vector out on the time reversal in both cases. So there could be an endless discussion. Is the anomalous Hall effect actually due to the weak relativistic magnetization or not? We know from theory that not, because we can switch the magnetization off and we still have the anomalous Hall effect. But that's not an experimental proof, right? That's our theoretical proof. But in a magnetic X-ray magnetic circular diachroism, we can actually do it. Because in diachroism, you have the spectrum. You do not have just one value. You have the entire energy spectrum. So we can look how the spectrum looks like in the same material when it's generated by the net magnetization, or how the spectrum looks like where the magnetization is weak experimentally. And it's completely different. So we did experiment here, not in this microscopy, but in the spectrum, in the absorption, X-ray circular diaphorism absorption. And we see completely different spectrum when we apply magnetic field and we really can the moments and generate a net magnetization. We have one spectrum, which is a typical XMCD spectrum of magnetic or ferromagnetic manganese. But when we switch off the magnetic field, we have completely different spectrum of XMCD, which is not consistent with a net moment, but is perfectly consistent with the Nail vector. And so from this, we actually know experimentally that we are not looking at magnetization, we're looking at the Nail vector.
Yeah, my question really is that
if
theoretical, right? You can turn the speed of light to infinity. Well, such an observation is still possible.
So I forgot what I was actually heading, I was heading to. So in XMCD, unlike anomalous Hall effect, where you need the time relative symmetry breaking and spin orbit for the same orbitals near the Fermi level, because this is what defines the anomalous Hall effect. Here, in XMCD, you can turn off completely spin orbit coupling for your valence orbitals, those ones that are responsible for magnetism.
Yeah.
You can turn it off, nothing changes, and you have exactly the same XMCD signal. The spin orbit coupling is enough to include in the core levels. So the nice thing about XMCD is actually you decouple the magnetism or the time relative symmetry breaking by magnetism, which is not related to spin orbit coupling, from spin orbit coupling, because that only contributes from the core levels.
Yeah. So you do need spin orbit coupling in the
valence.
Valence electrons.
I don't need that in the valence electrons, which are responsible for the magnetic order.
Okay. All right. Thank you.